Welcome back to the computer lessons.
Portable energy is the invisible chain binding our modern existence to the physical world, dictating the limits of our mobility. Without the ability to store electricity in a dense chemical format, your smartphone would be a stationary paperweight tethered to a wall. We have mastered the flow of electrons, but capturing them is a brutal battle. The lithium-ion battery is the heart of this mobility revolution, offering a high energy density that other chemistries simply cannot match. It is a complex electrochemical cell where energy is stored not as static charge but as potential within molecular structures. Understanding its chemistry is the key to mastering all modern portable engineering. Inside every cell, four primary components coordinate the movement of energy: the anode, the cathode, the electrolyte, and the physical separator. These components facilitate the controlled flow of ions and electrons, preventing chaotic discharge while maximizing storage capacity. Each material is chosen for its specific electrochemical properties and its long-term stability. The cathode, or the positive electrode, is typically made of a lithium metal oxide, acting as the primary source of lithium ions. Common materials include lithium cobalt oxide or lithium iron phosphate, each offering a different balance of capacity, safety, and cost. The cathode dictates the total voltage and energy potential of the battery cell. Opposite the cathode sits the anode, or the negative electrode, which is almost universally made of layered crystalline graphite. Graphite is chosen for its unique ability to host lithium ions within its molecular layers without changing its physical shape significantly. This structural stability is what allows the battery to be recharged thousands of times effectively. Between these electrodes lies the electrolyte, a chemical medium that allows lithium ions to travel back and forth during cycles. This is usually a lithium salt dissolved in an organic solvent, designed to be highly conductive to ions but insulating to electrons. If electrons could pass through the electrolyte, the battery would short-circuit internally. To ensure electrons only travel through the external circuit, we insert a thin, porous polymer film called the separator. This membrane allows tiny lithium ions to pass through its microscopic pores while physically blocking the much larger electrode structures. The separator is a critical safety component that prevents the two electrodes from touching directly. When you use your device, a chemical process called intercalation occurs as lithium ions move from the anode to the cathode. Electrons are forced to travel through your phone's processor to reach the other side, providing the power needed for computation. This movement of ions is a physical migration through the internal liquid medium. During the charging process, the electrical pressure from your wall charger forces the lithium ions back into the graphite anode. This stores energy by creating a high potential state, essentially packing the ions into the graphite lattice against their natural inclination. The battery is now a loaded spring, ready to release that stored potential. A crucial but invisible feature of a healthy battery is the SEI layer, or solid electrolyte interface, formed during the first charge. This passivating layer protects the anode from reacting too aggressively with the electrolyte, ensuring a stable environment for ion transport. Without a well-formed SEI layer, the battery would degrade in just a few cycles. However, lithium-ion chemistry is inherently volatile and sensitive to extreme temperatures or physical damage that might occur during use. If the separator fails, a massive internal short circuit triggers a phenomenon known as thermal runaway. This is a self-sustaining feedback loop where heat causes more chemical reactions, leading to fire or an explosion. To prevent such disasters, every modern battery is managed by a dedicated computer chip called the Battery Management System. The BMS monitors voltage, current, and temperature in real time, acting as a digital bodyguard for the chemical cell. It will instantly disconnect the battery if it detects a dangerous surge or overheating. The physics of lithium-ion cells dictates a nominal voltage, usually around 3.7 volts for a single cell. As the battery discharges, this voltage drops slowly until it reaches a cutoff point, typically around 3 volts. Your phone displays 0% at this point to prevent the cell from becoming permanently damaged. Energy density is the primary metric we care about in portable tech, measuring how much power fits in a kilogram. Lithium is used because it is the lightest metal and has the greatest electrochemical potential. This allows us to fit massive amounts of work into a thin smartphone that stays comfortably light. But every battery has a limited lifespan, degrading slowly with every single charge and discharge cycle that it completes. This degradation is caused by side reactions that consume the available lithium or thicken the internal SEI layer. Over time, the internal resistance increases and the total capacity to hold a charge drops significantly. A major cause of sudden battery failure is the growth of lithium dendrites, which are microscopic needle-like structures of metal. These dendrites can grow through the separator, eventually touching the cathode and causing a dangerous internal short circuit. Modern research focuses on creating solid-state electrolytes that are physically strong enough to block these growths. Charging a battery is not a simple linear process, but a two-stage protocol known as CC and CV charging. The first stage is constant current, where the charger pumps in as much power as possible to reach 80%. This is why your phone charges very quickly during the initial 30 minutes. Once the battery hits a specific voltage threshold, it enters the constant voltage stage to safely finish the charge. The current is slowly reduced to prevent the voltage from overshooting and damaging the delicate internal chemistry. This is why that final 20% of charging always seems to take the longest time. Depth of discharge, or DOD, is another critical factor that determines how many years your battery will survive. Draining a battery to absolute 0% places immense mechanical stress on the graphite and metal oxide structures. Keeping your battery between 20 and 80% can often double the total number of usable cycles. Heat is the ultimate enemy of battery longevity, accelerating the chemical decomposition of the organic electrolyte and the solvent. Fast charging generates significant heat, which is why your phone feels warm when plugged into a high-wattage brick. Modern chargers communicate with the device to balance speed with thermal safety and long-term health. Battery capacity is measured in milliamp hours, or milliamp hours, representing the total amount of charge the cell can deliver. However, watt-hours is a more accurate measure of total energy, as it accounts for the voltage of the system. Manufacturers often use thin, pouch-style cells to maximize every millimeter of space inside a chassis. We are currently reaching the theoretical limits of what traditional liquid lithium-ion chemistry can achieve in terms of density. To move further, engineers are experimenting with silicon anodes, which can host 10 times more lithium than graphite. However, silicon expands significantly when charged, often cracking the anode and destroying the battery cell quickly. Solid-state batteries represent the next major leap, replacing the liquid electrolyte with a solid ceramic or polymer layer. This would eliminate the risk of fire and allow for much higher energy densities without the stability issues. While currently expensive to manufacture, they are the future of electric vehicles and high-end electronics. Recycling lithium-ion batteries is a complex and expensive logistical challenge that the world must solve to remain sustainable. They contain valuable materials like cobalt, nickel, and copper, but they are difficult to disassemble safely without causing fires. Developing a circular economy for these materials is essential for the future of the technology. Beyond the chemistry, the physical design of the battery must account for the mechanical swelling that occurs naturally. Lithium ions physically push the graphite layers apart, causing the entire battery to grow in volume by several percent. If a case is too tight, this pressure can damage the screen or motherboard internally. We have mastered the storage of chemical energy, but we must also master the interface that uses it. The battery provides the power, but your interaction with the machine is what makes it a tool. Every component we have discussed so far relies on this stable flow of chemical power. In our next instructional video, we will explore the physics of touchscreens, comparing capacitive and resistive technologies to see how glass feels. We will decode how your finger creates a change in an electric field to move the digital cursor. We are moving from power to the ultimate interface.
The battery is a consumable heart that degrades with every single breath it takes for your digital world. Knowing the science allows us to extend its life and improve our designs for a more mobile future. Tell me in the comments, do you charge your phone to 100% every night? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.